So today, we're diving into something really cool, a brand new way to train AI. We're talking about a strategy that helps an AI solve these ridiculously complex physics problems. You know, the kind you need for designing hypersonic jets or creating super accurate weather models. These are problems that usually make even our best AIs just give up. So yeah, let's get into it.
I mean, just think about that for a second. What if you could give an AI a problem so hard it's like trying to predict every single swirl in a hurricane, but instead of just failing or spitting out a nonsense answer, it could actually recognize, hey, this path isn't working, and then figure out a new way to attack the problem, all by itself. That is the big idea we're exploring.
All right, so to really get what's going on here, we first have to introduce the hero of our story. And we're not talking about your average AI. This is a special kind of model that basically has the laws of physics baked right into its code from day one.
It's called a physics-informed neural network, or a PINN for short. And the best way to think about it is this. A regular AI learns from looking at tons of data, right? Well, a PINN does that too, but it also has to follow the fundamental laws of physics, like gravity or how fluids move. It knows the rules of the universe before it even starts.
And this is a huge deal. On the left, you've got the old school methods. They rely on building these super complicated digital grids or meshes to run simulations. They work, but they can be incredibly clunky and slow. But on the right, you have PINNs. They don't need a mesh at all, which makes them way more flexible and honestly a lot faster, especially when you throw those messy, high-dimensional problems at them that make traditional methods just, well, choke.
But here's the thing. Even this super smart, physics-savvy AI has a weakness, a kind of Achilles heel. There are certain problems out there that can trip it up and send it down a rabbit hole to a completely wrong answer.
Exactly. It sounds a little too good to be true, doesn't it? So what is the catch? Why do even these advanced AIs get stuck when the going gets tough?
Well, the villain of our story has two names, stiff problems and local minima. Stiff problems are basically scenarios where things are changing on wildly different scales at the same time, like the chaotic turbulence over an airplane wing. And these problems create these sneaky little traps for the AI called local minima.
This hiker analogy is just perfect. The AI's job is to find the lowest possible point. That's the point with the lowest error, the best solution. But the problem's landscape is like a huge mountain range, full of little valleys and dips. The AI can easily wander into one of those small valleys, see that it's the lowest point right there, and think, aha, I found it. It stops looking, totally clueless that the real answer, the Grand Canyon of solutions, is miles away.
And you can see that exact problem happening right here. This is a standard PINN trying to solve a fluid flow problem. After 140,000 tries, its answer is just wrong. It doesn't look right at all. But here's the wild part. The AI is totally convinced it's doing a great job. Its internal score, its loss, keeps getting better, telling it, you're on the right track, keep going. It's stuck in that little valley, and it's confidently digging itself deeper.
So how do you rescue the AI from that trap? Well, researchers developed this incredibly clever, almost simple solution. It's a strategy that basically gives the AI a get-out-of-jail-free card, letting it jump out of a dead end and search somewhere new.
It's a two-step move called re-initialization. First, the AI learns to spot when it's getting stuck, when parts of its calculations just stop improving. And then, once it finds one of those stagnant spots, it does something that sounds crazy. It just hits the reset button on that one little area, feeding it new random values. It's like taking an Etch-a-Sketch, shaking clear just one little corner of the picture, and forcing itself to try drawing something totally new there. And this whole thing is built into a two-phase training process. The first phase is all about exploration. Now, the training looks pretty chaotic and messy during this phase, but that's the point. The AI is sending explorers all over the mountain range, jumping from valley to valley, looking for the deepest one. As soon as one of those explorers finds a really promising deep canyon, phase 2 kicks in, fine-tuning. The resets get turned off, and the AI focuses all its energy on carefully climbing down to the absolute bottom of that canyon to find the perfect answer.
Okay, so the theory sounds amazing, right? But the real question is, does it actually work in practice? Let's check out the results and see how this new and improved AI stacked up against the old versions.
And the results are frankly stunning. You're looking at a classic, really tough fluid dynamics problem. The older models, they just couldn't nail it. They missed some really important details. But the new version, the RI-PINN with the re-initialization trick, it got it almost perfectly. It captured the big vortex in the middle, sure, but it also correctly modeled the subtle, tricky, stiff flow right up against the edges, which is exactly where the old models would always fail.
The numbers here tell an even crazier story. That mean square error column is just a fancy way of saying error score. The lower, the better. The old naive PINN had an error score of about 0.05. The new RI-PINN, our hero, its error is down at 0.000225. That is not just a little bit better, that's over 200 times more accurate. It's a completely different league.
But this is the real kicker. That number, 90,000, that's how many training cycles it took. The old model spun its wheels for 150,000 rounds and still got the wrong answer. Our new, smarter AI found a vastly more accurate solution in almost half the time. It's not just better, it's way more efficient.
So yeah, this is way more than just a clever coding trick. This is a fundamental shift in how we can approach problem solving with AI, and it has some seriously big implications for science and engineering.
This visualization just says it all. The old AI's journey is short and straight to the wrong answer, that little valley it got stuck in. But now, look at the red path. That's our new AI. It wanders all over the place. It explores this huge landscape of possible answers before it finally locks onto the true, correct solution. That messy, chaotic-looking journey is the entire secret to its success.
The researchers themselves summed it up perfectly. This isn't just about tweaking an old tool to be a bit more accurate. This is about blowing the doors wide open, letting these AIs tackle a whole new class of problems that we used to think were just too hard for them. And really, that's the thought I want to leave you with. We've managed to teach an AI a very human skill, knowing when you're stuck and being brave enough to try something new. If that can help it solve chaotic fluid dynamics, what else could it do? Unraveling the mysteries of protein folding? Discovering brand new materials? Building climate models that are actually reliable? What impossible problem do you think an AI that knows how to get unstuck should tackle next?